What if a few thousand lines of code quietly broke machines worth millions without a single missile fired? In 2010, researchers discovered a stealthy worm that didn't steal files. It targeted industrial controllers and changed physical behavior. Engineers at a uranium enrichment site saw healthy screens while machines self-destructed. This wasn't vandalism or ransomware. It was precision sabotage aimed at centrifuges. The discovery forced a rethinking of security. Code could now move from screens into shafts and rotors. But how did software jump isolated industrial systems and hide the damage? Call it the first widely recognized cyberweapon. Stuxnet was a worm that targeted Siemens Step7 engineering stations and S7 PLCs. It didn't ransom data or spy for months. It altered control logic and spoofed sensor readings to fool operators. The result? Centrifuges endured stress cycles and failed gradually. That subtlety made the attack surgical and hard to detect. If malware could fake reality, defenders needed new tools. So what precise mechanisms made that possible? Step 1. Entry. Stuxnet used multiple zero-day exploits, including a shortcut vulnerability that ran code just by viewing an icon. A USB drive became the Trojan horse. It also carried signed drivers stolen from legitimate companies. That reduced suspicion and let code run without alerts. In short, the authors combined software flaws with predictable human habits. The air gap wasn't a wall, it was a gate left open by routine work. Next, how it moved inside networks. Once on a Windows machine, Stuxnet behaved like a surgical worm. It scanned for Siemens Step7 software and particular PLC communication signatures. If it found the right environment, it escalated privileges and hid. If not, it often lay dormant. That selective aggression limited collateral damage and increased mission success. Think of it as a locksmith who only acts when he finds a specific lock. But finding those locks required lateral movement, and that's where stealth mattered most. The stealth layer was the trickiest part. Stuxnet intercepted engineering software calls and recorded normal sensor streams. When it activated the sabotage, it replayed those recordings. Operators watched plausible readings while centrifuges experienced destructive cycles. The worm even added safety checks to avoid obvious anomalies. This level of deception meant human trust became a vulnerability. You'll see how those fake readings translated into physical stress on machines next. Stuxnet included strict targeting rules. It searched for specific frequency converters and process signatures associated with uranium cascades. If conditions didn't match, the worm often stayed idle. That restraint lowered odds of discovery and diplomatic blowback. Yet the worm still propagated beyond its intended scope, showing how self-replicating code always carries risk. This tension between precision and contagion shaped later cyber operations and created new challenges for defenders. So how did Stuxnet reach a supposedly air-gapped facility? Investigations pointed to contractor laptops, USB drives, and supply chain touchpoints. Someone moved files between environments. That human bridge turned isolation into vulnerability. Air gaps slow adversaries, but don't stop motivated actors who exploit routine maintenance. The lesson: security must assume some connection exists. Next, we'll explore who likely sponsored the operation and why attribution matters. Attribution is messy in cyberspace, but evidence and reporting pointed to a state-backed campaign codenamed Olympic Games. Complexity, intelligence gathering, and tailored hardware knowledge suggested nation-state resources. Whether or not every detail is public, the operation blurred espionage and warfare. It showed how digital tools can pursue geopolitical aims without kinetic strikes. That precedent changed policy discussions and military planning across the globe. But what exactly made Stuxnet different from previous malware? Stuxnet earned the label first cyberweapon because it produced measurable physical damage. It combined process deception, intelligence about a target facility, and operational discipline. The worm didn't just cause outages. It engineered equipment fatigue while hiding its tracks. That combination forced a change in how industries and governments think about threats. Before we recap briefly, keep in mind this shift affected both technology and policy in profound ways. Mid-video recap. Stuxnet infected via USB and 0 days, moved quietly inside Windows environments, spoofed sensor data, and injected PLC logic that damaged centrifuges. It used targeting checks to limit obvious spread and likely had state sponsorship. That summary sets the stage for the deeper technical anatomy, the 3 brains that made the operation possible, and the defenses those brains exposed. First brain, the Windows worm. It propagated through USB, local networks, and 0-day exploits. It validated environment details and used stolen certificates to appear legitimate. That made detection by traditional antivirus unlikely. Second brain, stealth mechanisms that hooked into Step7 and hid files. Third brain, the PLC sabotage logic that timed rotor speed cycles to cause mechanical failure. Each brain played a distinct role, and defenders had to design 3 different counters. Next, we'll unpack the PLC logic itself. PLC manipulation was surgical. Stuxnet injected ladder logic and function blocks that analyzed process behavior before acting. It waited for signatures that matched enrichment cascades. Then, it launched timed speed changes while replaying recorded telemetry. This approach exploited operators' trust in displayed data and in maintenance procedures. The result: hardware degradation that looked like normal wear. That technique taught defenders they must watch PLC logic changes, not just server logs. Stuxnet's legacy rippled across the threat landscape. Families like Duquay and Flame reused reconnaissance and stealth techniques. Later attacks targeted power grids and transport systems with different aims. The key trend: advanced tactics diffuse over time. A capability first used by one actor can inspire others. That reality means defenders should assume adversaries eventually adapt and scale similar methods. What can operators do to reduce that risk in practice? Start with engineering-first security. Know the physical process and map critical assets such as PLCs, HMIs, historians, and engineering stations. Build a digital baseline of normal traffic and process metrics so anomalies stand out. Assume someone might cross an air gap. That mindset shifts investment from perimeter firewalls to deep process visibility. Up next, hardening network design and practical controls that block the common paths attackers used. Harden the ICS network, segment aggressively with zones and conduits, control removable media tightly, and maintain staged patching plans. Lock down engineering workstations with whitelisting, least privilege, and tamper-proof logs. Secure remote access with jump servers and strong authentication. Those controls address the exact weaknesses Stuxnet abused. But detection also needs upgrades. You can't defend what you can't see, and visibility must include PLC-level behavior. Myths linger. No, air gaps don't guarantee safety. No, antivirus alone wouldn't have reliably caught Stuxnet. No, it wasn't just a Windows problem. PLC logic was the heart of the attack. Attribution isn't simple either. These myths lead to dangerous complacency. Understanding nuance helps prioritize defenses that actually reduce risk. Now let's walk a fast timeline to see how the operation unfolded and how the community responded. Timeline in brief. Development likely began years before 2010, with strange centrifuge failures reported in 2009. Samples reached antivirus vendors by mid-2010, sparking deep analysis. Public reporting over following years connected the operation to state actors. The long-term effect was an acceleration of ICS security practices across industries. That pace of change still continues, driven by both policy and technical innovation. But the ethical questions remain, and they're thornier than technology alone. Ethically, Stuxnet raised hard questions. Does a covert cyber operation that avoids bloodshed but damages infrastructure set a dangerous precedent? How do nations define use of force in cyberspace? The attack showed how deniability and controllability can be designed, yet risks of unintended spread persist. These debates influence treaty talks, defensive investments, and corporate risk planning. Finally, if you're curious about bathing skills, here are safe, practical next steps. If you want to learn ICS security, study PLCs, SCADA, and industrial protocols like Modbus and DNP3. Use lab sandboxes and simulators, not live systems. Follow NIST SP 800-82 and ISA IEC 62443 for best practices. Track advisories from vendors, certs, and CISA. Map threats to defenses with frameworks like MITRE ATTAK for ICS. These steps build practical skills while staying ethical. In the final scene, we'll summarize the stakes and the single urgent action to take now. Bottom line, Stuxnet proved code can break things. It blurred IT and OT and rewrote cybersecurity priorities. The practical checklist is clear. Inventory assets, segment networks, control engineering access, and detect PLC-level anomalies. Train operations and security together. Build golden images and test responses. The best time to start was years ago. The second best time is today. If you want safer critical systems, act now and spread the knowledge, because silence benefits adversaries. If this breakdown helped, like and subscribe for deeper security explainers, and tell us in the comments what ICS topic you want unpacked next.